The most important foundation of our hobby is this. Or rather, this. Hi Astro Addicts, Tim here. Today I want to take advantage of these cloudy skies and take you on a small trip through our universe. This sound might be very familiar to you. It's the sound of a tracking mount following the movement of the night sky. But how fast is this actually, and what does it track? For this question we need to zoom a tiny bit out. Just a tiny bit out. This is Earth, as seen by astronomers. Flat and boring. From here we see the stars moving overhead, revolving around the north and south celestial pole. But this is of course our limited view. From the perspective of a distant observer, the Earth is spinning, and the stars remain basically stationary. These stars are so far away, they will remain stationary no matter how we move in our journey around the Sun. Let's call these fixed stars, or just distant stars. We will mark the position of an observer on Earth with a small line. This observer will see a distant star, and after one day he will see that star in the same position as before. Or will he? But what is a day? Asking most of the population on this flat Earth, most of them will probably say 24 hours. But that's not true. To get the distant star back into yesterday's position, the Earth needs to spin exactly 360 degrees. And this time are not 24 hours. It's precisely 23 hours, 56 minutes and 4.0905 seconds. This time is called a sidereal day. It's the time deep space objects, basically everything outside our solar system, needs to turn one time around the Earth. Apparently around the Earth. Let's get the Sun into this. This observer will now see the Sun at the maximum height in the sky, noon. And in one day he will see it there again. Or will he? Within one sidereal day, the Earth also moves around the Sun, which means in order to get the Sun back to its maximum in the sky, Earth needs to spin this tiny bit more. More rotation is required to compensate the path around our star. The distance Earth is moving around the Sun in a day is roughly 1 degree. This 1 degree will take more time than the sidereal day, about 4 minutes. I say about 4 minutes because there are way more variables to consider. The orbit around our Sun is elliptical and the gravitational forces from other planets cannot be neglected. On average, such a solar day will take 24 hours. The tracking mount you use, hopefully on every clear night, has different speeds at which it can track the night sky, or the Sun. Sidereal rate will focus on distant stars. If you hear this sound, if you want to image deep space objects, that's the speed you want. But how much speed is that? The sky is divided into 360 degrees. Each one is divided into 60 arc minutes, again divided into 60 arc seconds. In one sidereal day, there are 23 times 3600 plus 56 times 60 plus 4.0905 seconds. The sidereal tracking rate are 15.04 arc seconds per second. Solar tracking, on the other hand, is much easier. 360 times 3600 divided by 24 times 3600, or just 360 over 24. This means that the sidereal rate is only 0.04 arc seconds per second faster than solar tracking, 15 arc seconds per second. So next time you are outside, preparing your equipment for a night of deep space imaging, think about the wonderful motion you're about to witness. This time determines the ratio of gears in your mount. It determines the time you need to expose your time-lapse images, and the time we have to capture images of this wonderful universe. These 23 hours, 56 minutes and 4 seconds are our way of living life.